Okay, good afternoon, everyone. We're very happy to have today's GTP seminar by Chris Kapulkin, who's going to tell us about the calculus of fractions for quasi-categories. And this is the first part of a series of two talks. The second one will be given by Daniel next week. Chris, please.
Awesome. Thank you so much for the introduction. Thank you for the invitation. It's been, I think, almost 10 years since the last time I spoke in Hisham's Geometry, Topology, and Physics seminar. And I very fondly remember those seminars from my days as a grad student. Just to give you an idea how it was back then, I don't know how it is now, but we had some outside speakers, and other than that, a lot of talks were given by us grad students, and we often spoke about things that we were just learning. And the audience was very diverse. So there were some category theorists, but there were some, low-dimensional topologists. And I think this seminar was actually the strongest influence in shaping me as a speaker and making me think through how to reach a broad audience or a specific audience of the talk, where I want to say certain things, but how do I get there in a way that's comprehensible to people as different from me as low-dimensional topologists. I think very fondly of those seminars, and so it's a great pleasure to be back, even just virtually.
Very good to have you, Chris. And equally diverse, by the way.
That's fantastic. Okay, so good for everyone in the room there.
Right.
Yeah. So today I'm going to give a talk about joint work with Daniel Carranza, who was an undergraduate at Western and now is at Hopkins, working with Emily, and Zach Lindsay, who was a postdoc at Western. And so it's a piece of work that I really like. I enjoy talking about it. And as far as I understand, it has applications to a lot of different things. And I hope you'll help me find more applications, because applications that we found are as diverse as string topology. So that's actually not something that we found. It's something that Andrew Blumberg and Mike Mandel found, and combinatorics. That's something that Daniel and I have been working on. So, that's the goal. And the last thing is, as Hisham mentioned, this is the first talk in the two-part series. So my job, as I see it, is introduce a lot of background, and then Daniel will actually prove actual theorems. And so if you get a sense in this talk, it's not going anywhere, it won't, right? That will not change. This talk will not go anywhere, but tune in next week to see where it's actually going. Okay, so let me start by talking about what I love to talk about, which is what is the goal of homotopy theory. And for me, homotopy theory, as anything else, is always abstract. So I'm going to talk about the goal of abstract homotopy theory. Okay. So as far as I can tell, the goal of that is to understand the localization of a category at the class of weak equivalences. Okay, so what does that really mean? Well, you have some category, you have some class of maps in it that you want to think of isomorphisms, but they are not isomorphisms. You want to formally invert them. And so the first reference that I'm aware of for this kind of stuff goes back to the 60s, and it's a book by Pierre Gabriel and Michael Zisman on calculus of fractions and homotopy theory. So this is from 1967. That's been a while since then. So what do they do in this book? Well, so they start by introducing the notion of a marked category. They don't call it a marked category, but I will give them credit for almost introducing the name. So a marked category is a category C with a collection of maps, a class of maps, W, and we call them weak equivalences. Okay, so that's a thing. And as I said, this is something that we encounter all the time in homotopy theory. So topological spaces with weak homotopy equivalences, spectra, we have stable equivalences, you name it. And what we want to understand is we want to understand the localization of that category of the class of weak equivalences. So the localization, also known as the homotopy category of CW, is a category CW inverse with a functor gamma from C to CW inverse such that gamma takes all the weak equivalences to isomorphisms, and it's universal functor with that property. And for any functor with that property, for any f from C to D, such that let's see, f of W is contained in isomorphisms, there is a unique f bar from C W inverse to D, such that f bar composed with gamma is isomorphic, naturally isomorphic to f, and it's uniquely naturally isomorphic. So here is C, here is C W inverse, that's the localization, and here is f, go to D, and that's the functor that must exist uniquely. And of course, unique is up to unique natural isomorphism, so I can say here. So if I can introduce my favorite piece of notation, it exists and then it's unique up to isomorphism. So it's a little, yeah. Okay, and one other way of saying it, is that, well, if I take functors from C W inverse to D, I can of course precompose with gamma to get a functor from C to D. Okay, and now among these I can pick a subclass. Maybe I'll call it, so these are functors with f of W being contained in isos, right? And I require that this thing B is an equivalence of categories. Okay, and the first theorem that those guys prove, those guys are Gabriel and Zisman, is that this thing always exists. So CW always exists And the proof is very simple. We take a push out in the category of small categories. They push out in cat. So here, of course, you have to be careful, right? Like small, large, but it's a very simple push out, right? So you have your weak equivalences, and weak equivalences sit inside of C via this coproduct. Here, 1 is my poset with 0 less than or equal than 1, and this embeds into what I would call E1, and E1 now is a poset, or sorry, it's no longer a poset, it's a preorder. So it now has two objects. Maybe we can still call them 0 and 1, but now there's an isomorphism between them. So there are maps going both ways. And we take this push out, and this push out just glues in all the inverses to everything. And we're done. This exists. So great. So we now understand right, localizations of all marked categories. So our job is done, except it isn't, because what we just did is what I said we did. Namely, we took a push out of categories, and push outs of categories are unworkable. So let's just record that. This is unworkable. So it involves things like, you know, in order to get a map from X to Y, I may need to go forward in the category C, but then maybe I need to go back, and I go forward, and I go back with a weak equivalence, and you know, eventually I arrive at Y, but the process may involve zigzags like so of arbitrarily long size, and that's you know, simply not a good idea. So they say, well, that's too bad, but maybe if we impose further conditions on the class W, we can learn something. And if you one way of, I guess, dealing with this problem is through model categories, right? So in model categories, we come up with two more classes of morphisms, namely fibrations and cofibrations, and then we can often say something more reasonable about the localization. However, we are 2 years away from the publication of Quillen's homotopical algebra, right? And I guess election of Nixon. So they propose a slightly different solution, and that is calculus of fractions. So they say the following. So they say that CW satisfies calculus of left fractions, which I think I misspelled in the title. So it's going to be denoted CLF for reasons that are probably clear, if the following three conditions are satisfied. So the first condition is that W is a wide subcategory of C. So what that means is it contains all identities, and is closed under composition. Closed under composition. Okay. Number two, for any span like so, I have a span in which one leg is a weak equivalence, right? So I have three objects, two morphisms, and one of those morphisms is a weak equivalence. There is a commutative square so I'll draw the original span, and now we can complete it to a commutative square like so, where we swapped the weak equivalence in some sense, right? So it's a way of yeah, it's a way of swapping, I guess, the weak equivalence to something else. And for the grande finale, so if FW is equal to GW for W in W, then there is V in W such that VF is equal to VG. And so the picture that you should keep in mind is that of I have two parallel morphisms here, F and G, and there is a weak equivalence W here, and this weak equivalence equalizes those two morphisms on the left. Then I can find a weak equivalence V that co-equalizes them. So now equalizes them on the right. And there's also the definition of, so these are all the conditions, and there is a definition of calculus of right fractions. So I'll just say it very quickly. So CW satisfies calculus of right fractions, CRF, if, well, C up, the opposite category, W up, satisfies CLF. So you just change the order of all, right? You invert all the conditions, right? Like you now start with a cospan and get a span, and you or commute a square, and you co-equalize versus equalize, and you get your calculus of right fractions. Okay, and with all of that as preamble, Gabriel and Zisman then prove the following theorem. So if CW satisfies CLF, then we can describe the localization quite easily. So the objects of the localization, those you can always take to be just the objects of C. But now, if I want to understand morphisms in the localization between any two objects, X and Y, all I need to do is I need to understand zigzags of length 2, and very specific zigzags. And here I can put Y prime and a weak equivalence like so, and I'm going to quotient it by a certain equivalence relation. And where this equivalence relation is given by, well, I'm going to say that a zigzag X, Y prime, Y is equivalent to, so I apologize for this abuse of notation. So tilde here is both the notation for weak equivalence and for an equivalence relation. I would love to blame someone else for this, but actually that I did that. So yeah. So if you're unhappy about it, then you actually should bring it up with me. But it was already brought up to my attention, and you can see the result, which is no change. Okay. And that's exactly why we should have tenure. Thank you. No, okay. That aside, okay. So when are two zigzags equivalent? So one I'm going to draw here. It's going to be a weak equivalence here, and the other one I'm going to draw here. That's going to be a weak equivalence, and now we're going to just put some Z in the middle, which apparently disappeared. Okay, so another zigzag like so, with maps like that, and so if there exists such a Z, making all 4 triangles commute, then I'm going to identify 2 zigzags. So this is awesome when you think about it. This is really, really great. And the reason why it's great is before we had to deal with zigzags of arbitrary length. Now we cut it down to zigzags of length 2. So yeah, so that's great. And what's the proof? Well, all I'm going to tell you is that how do you compose fractions? So we usually call these little things here. These are called fractions. So how do you compose fractions? And that I think once you understand this, you understand everything there is to understand about the theorem. So if you have a fraction from x to y, which is given by, let's say, y prime in the middle here, and then from y to z, which is given by z prime over here, well, I can use condition 2 to swap these things, right, and get a true map there. And then, so this came to me from condition 2, and now this composite will be a weak equivalence by condition 1, right? And then I still need to show a bunch of things, and that's where condition 3 will be used, where I need to show that this is a category and so on. But this is the main idea, right? That I can essentially compose fractions, and they remain fractions using these two things. And in fact, life is even better than what you might have expected. So they then go ahead and prove a theorem that is too good to be true, and yet it is. So if CW satisfies CLF, then first of all, gamma from C to the localization of C at W preserves finite colimits. Finite colimits. And second, CW inverse has whatever finite colimits C had. So that is a so somehow you can infer completeness or co-completeness properties of the localization from the completeness or co-completeness properties of the original category. And the proof, again, I'll give you just the main idea. The proof, if you unwind the definition of those mapping spaces here, those used to be able to do highlighting back in the day. Okay, maybe. Okay, if you unwind the definition of this and this equivalence relation, then what you're going to see is that the mapping spaces, or the mapping sets in this case, can be written as a colimit. So it's a colimit over the category Y down arrow W. So this is I'll tell you in a second what it is. Let me just finish this expression. So it is C X Y prime, where Y W is the category of it's a subcategory of the slice, under Y. So slice, it should say somewhere. Slice under Y spanned by weak equivalences. Okay. Yeah, so these are all the objects of that category are all the maps from Y to something that are weak equivalences, and then all the maps between those. And when you think about this category, the key observation is that YW is filtered. And so the result, essentially, when you start manipulating things, will come to you from the fact that filtered colimits commute with finite limits. And you have a finite colimit there in the statement, you pull it in the front and you swap something, and it becomes essentially an exercise in category theory 1. Okay, so at that point, your BS detector has to go off, right? Like, this is too good to be true. So let's acknowledge that up front. So this is too good to be true? Okay, why is it too good to be true? Sorry, someone just called my office phone, which I didn't even know that was a thing you can call. So we'll get to that later. Okay, so why is it too good to be true? Well, my favorite category is it's not my favorite category. Okay. I can't talk now. Is the category of topological spaces, and this category is complete and co-complete. But when you take its homotopy category, when you take its localization, I mean, this is quite well known to be a horrible category. Right? If you take weak homotopy equivalences, you invert those. This has almost no limits or co-limits, right? It only has or co-limits. It only has products and co-products. So that doesn't sound like so something seems off. And of course, the conclusion from this that you should draw is that weak homotopy equivalences and on topological spaces does not satisfy. Does not satisfy CLF. And indeed, maybe a remark that I would make is that all different homotopical settings satisfy CLF or CRF up to homotopy. And what it means, let me give you a specific example. So if C is either a co-fibration or a fibration category, then what I would call pi of C, pi of not with capital C. So it's a framework, something like a model category, right? The category of equivalence is vibrations, and then you can define path objects or cylinder objects, and you can talk about homotopy, and you can homotopy gives you some kind of relation on morphisms, and you can quotient by it, and that will not compute the correct localization because it just won't. Okay, but this is the naive. This is the what people call the naive homotopy category or the naive localization. Satisfies homotopy CLF, and that was or CRF. So depending on whether you did fibration CRF or co-fibration category CLF. So that was already known to Brown. So Brown introduced vibration categories, and I guess once you have one, you have the other. And in his paper, so it was his PhD thesis supervised by Quillen in 1972. He already talks about, and what is kind of the main issue, right? We should be thinking of homotopy limits and co-limits instead, rather than completeness or co-complete. But Gabriel and Zisman already knew that issue, and here is one result that they prove that I guess we generalize. So they prove the following. So they prove that if this marked category satisfies CLF and CRF, then I need one more assumption. And C is abelian, then CW inverse is again abelian. And so you can see where Gabriel-Zisman theorem could be applied. One such place would be something like the homotopy category of spectra, right, or some stable context where you have this abelianist assumption. So you might be interested in localizing spectra in the homology theory. That's in fact where it has found applications since. But a lot of the ideas in the proof are could be recycled to talk about homotopy limits and co-limits, and that's what I want to do next. So we're going to now abandon categories, not abandon them completely, but generalize them to quasi-categories, and then we're going to invent calculus of fractions for quasi-categories. So let me start by just very quickly reminding you that what quasi-categories are. So a quasi-category is a simplicial set X satisfying inner Horn filling. And what that means is, well, I have those lambda and k's, right? So they look like this, 0, 1, 2, let's say, and this embeds into delta 2, and this into X, and I have a filler like so. This must exist for every map like that. There will be a filler for 0 less than k less than n, and so the filler would represent a way of composing those one cells here. So this is the case. Oh, sorry, I think I wrote 2 here. I suggest my picture was so suggestive that it confused me. Okay, very good. So the prime example of a quasi-category is the nerf of a category. So if C is a category, then the nerf of this category is a quasi-category. So is a quasi-category, and here the nerf, let me just remind you, it's a simplicial set that at level n is given by the functors from the poset with n+1 linearly ordered vertices to C. Okay, so so n is this fellow. Okay, cool. So with that, we can now define so a marked quasi-category. Quasi-category is a quasi-category with a chosen set of one simplices, subject to no conditions at all. Okay, so just as for categories, we just selected some morphisms, now we're going to select some one simplices. That's the only difference. Okay, and so then we can define the localization. Mention the localization of such a thing. Localization of a marked quasi-category XW is again a quasi-category. X W inverse with a map gamma from X to X W inverse such that gamma of W is contained in equivalences of X W. So here I'll explain in a second what I mean by equivalences. But let me just finish the statement. So, and for all quasi-categories Y, we have that the simplicial set of maps X W inverse into Y, again, I can take precomposition with gamma, and here I can take the underlying simplicial set of the marked simplicial set of maps from X to Y with its natural marking. Okay, so there's a lot of explaining they need to do here, but is a categorical equivalence. Categorical equivalence. Okay, so what the hell happened here? So let's go here. So I need to tell you what. Oh, yes. No, I said everything. Okay. So I need to tell you what it means to be an equivalence. And here, when I talk about marked simplicial sets, right? What I mean is simplicial sets with those collections of markings that are selected. And here there is Y with its natural marking. So every quasi-category can be marked at the class of weak equivalences or its equivalences. So when I tell you what equivalences are, you'll know what this is. So let me just quickly tell you equivalence. I'll explain here. So a one simplex, I can view it as a map from delta 1 to X, is an equivalence if, well, I have delta 1, that's my F, going into X, and now this embeds into what I would call E1. So just like delta 1, the representable is the nerve of 0 less than or equal than 1, E1 is the nerve of 0 is isomorphic to 1. So it's almost right, it's the condition for being an isomorphism. And I say that it's an equivalence if such an extension exists. And so the maps that I'm considering here take all the elements of W here to equivalences, the true equivalences now of Y. Okay, and so this is like, if you unwind it, it's the exact same condition that we had before. And another theorem is then that the localization always exists. So X W inverse always exists. Always exists. And what is the proof of this fact? Well, it's the same proof as before. It's just now in simplicial sets. So we take a push out. So we have those delta 1s that mark our W in X, and we embed those into E1s, and we take the push out over here. And so that should be our localization. And hey, push-outs of simplicial sets, push-outs of pre-shift categories are very easy. So there's actually nothing left to do. We're good, right? Except we're not done because the result won't be a quasi-category. So then we need to fibrantly replace. And fibrant replacement is, of course, very hard. So once again, we arrived at something that's in general unworkable. Mark, unworkable. So in whatever little time I have left, I would like to tell you what our replacement for the calculus of fractions in the quasi-categorical context is. So I'll explain this, and then next week, Daniel will tell you how to use it to actually get workable models of localization and how to infer those kinds of properties that we would like of completeness and co-completeness of the localization from the properties of the quasi-category that's being localized. So I'm going to define two marked simplicial sets. So the first one will be, they have a lot of decorations. So it's L, but then it has 3 indices. There's star, there's N, and there's K, which is a lot, I grant you that. So it's going to be the nerve of some poset, and the poset in question is the poset.
Can I interrupt you for a second?
Sure.
Are we, is there any size issues here? Are we still assuming that W is wide, or could it be wide? So is this are we doing a large colimit here, or is there not any...
well, the colimit might be okay. So the colimit might be it will be a colimit in the same universe that you're in, right? Like in the universe that you like so if you're thinking of something like, you know, topological spaces, right? It's gonna be a like, so all topological spaces involved will have to be small to accord in the universe U, and the colimit will take place in the universe, you know, the next one up, right?
Yeah, if it's itself indexed by the universe, but aren't we? I mean, if this is like, are you assuming the quasi-category is small to begin with, maybe? Or?
Yeah, no. So yeah, so X has to be small and in some universe, right? So then W has to be small, and so then you're done, right? Like,
sure, yeah.
Oh, good. Sorry.
Well, yeah, I mean, all right.
I mean, so yeah, so
in practice, that's a huge issue, right? I mean, of course, you can sort of define it away, but like in practice, you want a large category in your universe and localize it.
I mean, so I feel like, you know, I don't want to sound like someone who does homotopy type theory, but I would say if you're perverse enough to assume ZFC, you might as well assume two Grothendieck universes.
No, that's fine, but I would still jump out. But anyway, okay, I see what you mean.
Yeah, so
I mean, in practice, it's a huge issue. Like, for instance, this was what Quillen actually solved with the model categories, that the localization there was guaranteed to be locally small with respect to your fixed universe, which was not previously the case with other methods, right?
Right. Well, yes, but no. So, yeah. So I'm assuming existence of two universes, so that it's not. Yeah.
Sorry, maybe I'll just jump in and say, like, so I think Chris is like, so if I'm understanding correctly, basically what Chris is saying is that, like, this is not a problem of definition. Like, when we're defining these things and like proving these results, kind of in the abstract, we can, like, you know, we work with like a universe kind of viewpoint, and the size issues are not a problem. But it is true. But like in particular, the theorem, like for instance, when you want to show co-completeness, there is some kind of size issue. Like you do need to give some kind of bound on the size of weak equivalences. And this is something, I mean, and as you already mentioned, like this is the same is true in like and Gabriel Zisman's results. So yeah, like, so I think it's not a problem of definition, but you are correct that like this is an issue that like, there is a size assumption when you want to use these results that you have to prove. And like, you know, that's something that we dealt with, for instance, when we were applying it to combinatorics. And at least in that instance, like the size assumption that you want actually turns out to be fairly straightforward to prove. But yeah, I'll just add that.
All right, thanks, Leslie.
Okay, very good. Okay, well, yes, we were talking about two simplicial sets that I'm now trying to define, or Mark simplicial sets. So the first Mark simplicial set will be the nerf of a poset. So it's a very weird poset here. So it's a poset of subsets of the set N that contain a fixed element K. I need to tell you what the marking is. So remember that right, like the zero simplices in this thing would be just subsets, and then one simplices would be inclusions of subsets. So I need to tell you when to mark an inclusion like so. And I'm going to mark those whenever the maximum of A0 is equal to the maximum of A1. Okay. And then I'll define L and K to be a subset, a simplicial subset of this, omitting the top element n. Okay, so let's just do an example or two of those things. So the first one is L21 into L21 star, which hopefully will look familiar once we draw it. Okay, so what are the subsets of the set 0, 1, 2 that contain 1? Well, there is 1, there is 1, 2, and there is 0, 1. And they have maps like so. Okay, and then if I take all the subsets, that will look like this. It will be 1, it will be 0, 1, it will be 1, 2, and there will be the whole thing, 0, 1, 2. And now what are the weak equivalences here? So remember, a 1 morphism is a weak equivalence if the maxima agree. So this is a weak equivalence, this is a weak equivalence, this is a weak equivalence, and I think I got all of them. So that looks a lot like one of the conditions in Gabriel Zisman, if you remember. Okay, then let's just do another example to see what is happening. We're going to do L22, L22 star. So now the subsets must contain 2. So the smallest will be 2. And now I can either add 0 to 2 or 1 to 2. And everything will be a weak equivalence. And here, on the other hand, I'm going to have 2, 0, 2, 1, 2, and 0, 1, 2. Okay, and everything is a weak equivalence. 2 is the largest element. Okay, in all of these things. Okay, so with that, I can tell you now the definition. So a marked quasi-category. I realize that I'm way over time. That never happened to me before. But I'll be last bit, okay? Marked quasi-category XW satisfies CLF if, and I'll call these conditions maybe 1A. So W contains all the degeneracies, 1B, yeah, so all the identities should be in it. W is weakly closed under composition. So that's rather interesting. So what does it mean to be weakly closed under composition? Well, so if I take 2 composable one simplices that are both weak equivalences, now what can happen is in a quasi-category, I can always compose them. And what I'm saying is that there will exist some composite that is a weak equivalence. So it's not necessarily the case that any filler for this inner horn will give me a weak equivalence, but it is the case that there will be some that will yield a weak equivalence. And so these 2 conditions are supposed to resemble, if we go back to Gabriel and Zisman, condition number 1 here. W contains all identities. So that's 1A is right, and then close under composition. That's our weak closure under composition. Oh my God, where am I? Okay. So going back to this, now conditions 2 plus 3 only get one thing. So I'm going to have fillers for L and K into L and K star, like so, going into XW. So I'm going to require that this exists for 0 less than k less than or equal than n. And so when you look at the drawings that we did here, you can see, for instance, condition 2, the completing the square with like swapping the weak equivalents and so on, is exactly encoded in this diagram. And maybe the theorem that I'm going to finish with is that if you have a marked category CW, marked category, then CW satisfies CLF in the sense of Gabriel and Zisman if and only if the nerve of C with W satisfies CLF in our sense. So the two CLFs are equivalent. It's a strict, it's a generalization of theirs to quasi-categories. And yeah, so maybe this, that's the theorem I want to finish with. But I guess just to tell you what's happening next, well, so in a week, I guess Daniel will say something about how this condition can be then used to compute the localization of a quasi-category of the class of weak equivalences and do a lot of other cool things with it that kind of are more homotopically meaningful than what Gabriel and Zisman maybe were doing. Obviously, their results are applicable, but perhaps now they are applicable to a much broader range of contexts. So, okay, I think I'll stop here. Thanks.
Further questions for Chris? David?
Thanks, Chris. Just to check, when you localize the a quasi-category, the nerve of a category as a quasi-category, you're not necessarily going to end up with the nerve of the localization, or you're not even
Absolutely not, no.
End up with something fully quasi-categorical.
Yeah.
But hopefully, if you zero truncate that, it's going to be the nerve of the localization.
Yeah, yeah.
Hopefully.
Yeah, that's what you should get. Yeah. But yeah, so the nerve, the localization of the nerve should not be the same as the nerve of the localization. Yeah, but yeah.
How does this end up comparing to something like the hammock localization?
Well, it computes it computes the localization. It isn't okay. So the hammock localization takes you from a marked category to a simplicial category, which then you can fibrantly replace and apply the homotopy coherent nerve and get a quasi-category. Or you can do the thing directly, as in you can just take this, you can just take the nerve of the category and do this localization that I described, and the result is like equivalent. I don't know if there's a direct map, but there's certainly a zigzag of like 5.
Thanks.
Any other questions? Okay, if not, let's thank Chris again for the nice talk.
Thanks.
And we look forward to the continuation with Daniel.
Yeah, so I apologize for the anti-climactic